Good morning, everyone. Thank you for being here. Today I have the pleasure to moderate this CMCC webinar, part of our webinar series. Stefano Materia is the presenter, working at the Climate Simulation and Prediction Division. Stefano has a PhD in geophysics from the University of Bologna and had a postdoc experience at NCAR in the US, has quite a significant experience on climate services and the interaction between land and atmosphere with the purpose of predictability. Is also very supporting the whole community in transforming science into usable and useful information for target users. Today we'll present the recent work on multimodal subseasonal forecast of spring cold spells, and we'll highlight why subseasonal forecasts can help and benefit the hazelnut agribusiness. So why is the business community benefiting from forecast overall? Before leaving the floor to Stefano, a few words about CMCC Foundation, which is a 14-year-old organization that turned into a foundation in 2015. CMCC is concerned with the scientific research on climate change and understanding how the climate system is interacting with society, both in terms of course, environmental features, but also the human interaction. CMCC is constituted as a network with different locations and different offices in different locations, among which there is Venice, where I'm based, Bologna, where Stefano is based, but also Viterbo, Capua, Lecce, Milano, and Sassari. It is organized in different research divisions, precisely 9. The one where Stefano is working is the climate simulation and prediction, while I'm based in the risk assessment and adaptation strategies. But the all divisions are all concerned with understanding really how climate can interact with society overall. The topics concern from modeling to policy, moving from adaptation of climate impacts to the mitigation of the causes. And we're also very active in the outreach activity, so I really encourage you to visit our publication in peer-reviewed journals, but also in publicly available, of course, and to the general audience documents. We have several events. This webinar series that is featured on a precise YouTube channel, but also education with a PhD and a master, and also other communication activities very actively also on social networks. Finally, to participate to this webinar in the form and posing questions to Stefano, both while he's talking and also at the end of his talk, you can use the Q&A session, of course, but also the question menu provided by your system on the GoToWebinar, which means that basically you can pose and write down all the questions and we will look at them. If Stefano doesn't have time to address all the questions will be delivered to him, which means that he will be able to address them privately over email later on. Just a moment to advertise the forthcoming CMCC webinar, which is part of the Clara webinar series, where Clara is a European project focused on climate services. The idea of this forthcoming webinar on November 12th is to explore climate services for agriculture in the field of course, ARPAE with water requirement of irrigation, and Irriclime, which is a service developed by a private company, Gecosistema. So I leave the floor to Stefano, and remember that you will have access to this webinar recorded on the YouTube channel that you can see here, or you can just look for a CMCC webinar in YouTube, and you can follow all the updates, of course, on our Facebook account or mentioning us on Twitter as @CMCCClimate. I leave the floor to Stefano. Whenever you're ready.
Thanks a lot, Francesca. So the study basically generated from a collaboration that we had with a big player in the hazelnut agribusiness. And so they came to us with a very difficult question. They came to us asking if it was possible to predict cold spell at the beginning of the spring. And in the beginning, we looked at each other and like, like we're a little bit puzzled because it's a really hard question for, who tries to forecast the climate, because cold spells are very, like confined events in space and time. But then we started, developing a framework in order to understand how to do this. So this is the area of global production for hazelnut. We can see that most of the places where hazelnuts are cultivated lie in the Mediterranean climate. And so we have, of course, Italy and Turkey, which are the main producers, but also Spain and other regions that are outside the Mediterranean, but that share with the Mediterranean the type of climate. And we can see from this cake graph that most of the production, actually almost 70% of the global production, is based in Turkey. So this can pose some problems, because the area of Turkey where the hazelnut grow, which is this one in dark brown, facing the Black Sea, is basically very sensitive to many climatic events, such as summer droughts, heat waves, and also cold spells during the spring. And the spring frosts and summer droughts are actually the main climatic factors that can strongly affect the production. In particular, spring frosts hit the flowers when they have just begun their development, and low temperatures may be destructive for the germination, basically destroying the opportunity for plants to fructify. And due to a late frost in 2014, about 60% of the harvest was lost. So this is a graph showing basically in time between the 1950 to 2012 the global price of the hazelnut kernel, because we want to see how climate variability actually may reflect to the price. And we can see that until the late 70s, basically the price of the hazelnut was very low because the global demand was low. But then it started increasing, and we can see that there are peaks and lows in these prices from the 80s to the 2010s. And these peaks are partly, of course, due to factors that are external to climate, like, for example, political factors. But there are some events, like the droughts in 1979, 1985, and 2003, that actually hit the orchards and basically led the price to go up like with these peaks that we can see here. And we can see that also a frost in 1993 that occurred at the end of April basically led the price to climb up to $4 per kilo for the first time in history. As I was saying, there was a particular event in 2014 that hit the orchards, actually a very limited part of the orchards, only the eastern part of the area where the hazelnuts are cultivated. But this frost, even if it was short in time and very confined in space, led the price to climb up to $10 or $11 per kilo, which is double the price as it was just before the event. So such price variability calls for the need to predict such impacting extreme event with a certain advance. And we can do this through targeted subseasonal and seasonal forecasts. So basically, the idea is to build a model that fills the needs of the hazelnut buyers. So a big player in the hazelnut business needs to purchase the good when the price is the lowest. So in a normal year, that would be right after the time of the harvest, when the farmers has to sell their products. And it's between mid-August and the end of September. However, in a year characterized by a severe cold spell during the blossoming time, so between the end of March and the end of April, the production could be strongly decreased. Here, we draw an artificial, basically, series of temperature anomalies with a severe cold spell happening at the beginning of April. So if the production is strongly decreased by this severe cold spell, the price paid in mid-September from the buyers could be much higher than usual. Then the forecast comes to help, because the availability of a trustful subseasonal prediction system may allow for the anticipation of these extreme events. For example, a subseasonal forecast starting on March 15th. Then, having the information from the forecast, the company can decide to purchase the nuts at the end of March, just after the forecast release, trusting the outcome on the forecast, basically increasing a little bit the cost of the purchase, but avoiding a big loss due to the occurrence of a cold spell. So, if the buyer does not make use of the forecast, every year he has to take a decision. Purchase the hazelnut in March without any information, because it does not make use of the forecast. But buying in March means buying at a slightly increased cost. And in this way, he avoids the risk of a damaging frost. Or purchase the hazelnuts in September at a lower price, but with the risk of a large loss in the event of a damaging frost. So in case A, basically, he will always incur a cost C. But in case B, he will experience a loss L only when the cold spells occur. So to make a decision basically for this year purchase, having no info on future weather, the buyer may look at past season. So being sigma, the fraction of frost per year occurred in the past, for example, 20 years, his average loss would be sigma L. So a loss only when the cold spell actually occurs. Then, the best strategy to put in place for this year comes from a minimization of expenses. So the expenses of having no info, it is the minimum between sigma L and C, and the buyer will decide according to this. Having a forecast, of course, may improve this result and lessen the bill for the buyer. So by using the March 15th forecast made in the past 20 years, it is possible to check how many times the prediction system was able to correctly predict a cold spell, when it was wrong, etc. So we can create a contingency table to summarize past events. So here we have frost that actually occurred in observation, and here we have frost that were forecasted by the system. So when the forecast was forecasted and it actually take place, we have a heat event. And when the forecast is forecasted and it doesn't take place, we have a false alarm. And when the forecast instead was not forecasted by our system, but actually it takes place, we have a missed event. Of course, in the case that nor the forecast, neither the observation detect a cold spell, we will have a correct negative. Every time, if we rely on a forecast, every time the forecast says there will be a cold spell, the buyer will incur in a cost, C. While instead, he will incur in a loss every time the forecast says there won't be a cold spell, and the cold spell, in fact, takes place. So trusting the sub-seasonal forecast, basically the average expenditure for the buyer would be the number of heat events multiplied by C, plus the number of false alarm multiplied by C, plus the number of missed events multiplied by L. So between this and this, of course, if the expenses given by the information of the forecast is lower than the expenses given by having no info, then the forecast holds an economic value. This is the framework in which we work. So, but to have a forecast that actually holds a value, we need to have a trustworthy forecast. And to build up a trustworthy subseasonal forecast system, we set up a multimodal using all the models participating in the subseasonal to seasonal prediction project, which is a project starting in 2015. Like the main work describing it, led by Frederick Vitartis on BAMS, is an article of 2017. And basically, it put together like 11 different models that runs for a longer period of time with respect to normal weather models, so like for 30 or 60 days. There are several initialization every month, 4 to 8, so once a week or twice a week. And it's very easy to use because all models share the same metadata and are led back to the same horizontal resolution, which is 1.5 regular grid. So we use 4 of the sub-seasonal forecast model in this framework. In particular, we use the Chinese model, the CMA, with 9 of its ensemble members, the UK Met Office with 7 ensemble members, the ECMWF model with 10 ensemble members, and the Meteo France model with 14 ensemble members. So in the end, we have a multi-system based on 40 ensemble members, and we run this multi-system in 3 start dates: March 1st, March 15th, and April 1st. So the forecasts are aggregated in weekly outputs for the following 6 weeks, and the reforecast period corresponds to the 1996-2014 19-year time frame. Why these years? Because these are the years that are common, the years of forecast in the past that are common to each of our 4 models. So the multimodal anomalies is composed of the anomaly of each model with respect to its own climatology, and no weight on the number of ensemble members is given to the multi-system. So the first thing we've done was to test the multi-system by calculating the global 2-meter temperature anomaly correlation versus the reanalysis. So the multi-system is, like we can see that the multi-system is comparable and in many cases more skillful than the single model. We can see it from here. These are maps of correlation for target week 2 and target week 5. Of course, we see that all the models are, like more skillful, like when the target is like closer to the initialization, so week 2 in this case with respect to week 5. And you see that the multi-system has like more, at least a comparable amount of area, like dark red, orange, or yellow. That means high correlation with respect to the other models. And we have areas in which the skill of the multi-system is higher than in many, like in all of the models. Of course, we wanted to see like this 2-meter temperature skill for the Turkish area, which is the one we are mostly interested in. And we look at it for each model, each star data, and each target week. Again, we see that the multi-system is often, if not always, the most skillful of the model. We can see it here. So here we have the 3-star date, March 1st, March 15th, and April 1st. And here we have an aggregation of the 3-star dates in order to reduce a little bit the noise given by, like a single initialization. And the multi-system is the black line. Here we have the correlation, and here we have the lead weeks. So the black line, if we concentrate only on the aggregated 3-star dates, we see that the black line is often the most skillful of the model, at least in 3 of the lead weeks. But in the other lead weeks is very close to be the best. The fact that we can see is that in the first 2 weeks, of course, the correlations are very high and they decrease pretty fast. Like the skill degrades quickly starting from week 3, and at week 5 and 6, basically, we have almost no skill in the Turkish domain. So the question is it possible to extract usable and useful information more than 2 weeks in advance, starting from such poor skill? To assess this, we designed a cold spell index. Instead of working on 2-meter temperature, we work on a specific index calculating in the 2 areas of hazelnut production, West and East Black Sea. So these 2 domains, though, are too small for a reliable interpretation of the sub-seasonal forecast outcome. And then we decided to enlarge them by selecting nearby grid points that share similar climate anomalies during the reforecast period 1996-2014. Hence, we calculated temperature correlation between each box representing the hazelnut farms and the surrounding grid points. We then obtain maps of correlation where regions with higher values basically share a similar climate to, like the nut farms described by these boxes. So we decided to retain only points where the correlation was higher than 0.85, so basically orange and yellow point, as points that actually represent the climate of the nut farms. And our cold spell power index is calculated in these areas. So just to make things a little clearer, this is a schematic of cold spell power index. So we have like our basically areas, our maps of correlation. So if the temperature anomaly correlation of the grid point is higher than 0.85, we keep the grid point as to calculate our cold spell power index. Otherwise, the grid point is discarded. So we obtain here a correlation map masked in which only the grid points that will enter our cold spell definition are actually drawn. And here we make a second decision. So if at least 20% of these grid points are colder than a certain cold spell threshold, we retain them as cold spell points. So this threshold is arbitrarily based to 10th percentile. So basically, if 20% of these points are colder than the 10th percentile, a cold spell is detected. Okay. At this point, we have like the magnitude of this cold spell, which is basically the average temperature of the cold grid points, and the extent of this cold spell, which is the fraction of points with temperature lower than the 10th percentile, which for construction must be higher than 20%. So the cold spell power index is basically the multiplication of extent and magnitude. So here we detect the cold spells in reanalysis. This is for like the 6 weeks starting from March 15th. So from like March 16 to 22 to April 20 to 26, and we have values for the Western Black Sea domain and the Eastern Black Sea domain. We can see that usually when a cold spell hits one of the two regions, it actually hits also the other one, and most of the time the two intensity magnitudes are more or less similar. But there are cases, for example here, in which only the eastern domain was hit by a cold spell for 2 weeks in a row, while the Western Black Sea was not hit by any cold spell. And this is the 2014 cold spell that is detected in the eastern part, but not in the western part of the domain. So this is instead the forecast probability of occurrence. So basically we have our 40 members, and this is like for each year and each forecast week, the fraction of ensemble members that actually are predicting a cold spell. So like this number, for example, means that 10% of our ensemble member is predicting a cold spell. So since we have 40 ensemble members, that means that 4 of them are predicting a cold spell. But this forecast is probabilistic, so a choice is required. How high must the forecast probability be to trigger a cold spell alarm? So in other words, do we consider a forecast of cold spell one for which for example, CSPI has a 15% chance of occurrence? So how do we say that this blue value actually is a hit event, this is a correct rejection, this light blue is a missed event, and the red ones are false alarms? So to assess this, we basically make use of this Garrity Skills course. Garrity assigns a value to the 4 possible combinations between the forecast and verification, those hit, false alarm, missed events, and correct negative that we saw before. So for example, the hit event, for the hit event, the value is 1 minus the chosen threshold, which is the 10th percentile, divided by the threshold itself. So it's basically 9. And for the correct rejection is 1 on the score for the hit event, so 1/9. So basically, for every hit event that we get, we have, like we score a 9. For each of the correct negative that we get, we score a 1/9. And for the missed event and the false alarm, we score a -1 following Garrity. But still, so to understand whether, for example, this 35% is actually a forecast of cold spell, that would be a hit in this case, or not a forecast of cold spell, which would be a missed event, we need to set another threshold. And a threshold above which a forecast is actually a forecast of cold spell. Okay, so to do this, basically we set this lowest probability limit. So by basically maximizing the scores of our Garrity Skills scores, like summing these scores and maximizing the scores, moving this lowest probability limit, we obtain like the lowest probability limit that is actually the one above which the forecast is actually a forecast of cold spell. So in this case, for example, having a limit of 11.6% means that all the forecasts above 11.6% are actually a forecast of cold spell. So in this case, we have 15% of our ensemble members that are predicting a cold spell. So this is actually a forecast of cold spell higher than 11.6%, but it is a false alarm because the cold spell actually did not take place in reality. So by using like this methodology, we basically obtain our tables of contingency for each of our region, West and East Black Sea, and for each of the target weeks, for week 1 and 2, week 3 and 4, and week 5 and 6. So for example, for the Western Black Sea, weeks 1 and 2, basically we have 14 hit events in which the frost was predicted by the model and actually took place in reality. We have 9 false alarms in which the forecast actually predicted a cold spell that didn't take place. We have 6 missed events in which the forecast said we won't have a frost, but the frost actually occurred in reality, and we have 85 correct negatives. So if we remember our cost-loss model, the expense paid by the buyer using the forecast was this, and having no info was this. So if the forecast, if the expense trusting the forecast is lower than the expenses paid by having no info, then the forecast holds an added value. So basically, we go multiplying 14 by the cost, the false alarm by the cost, and the missed events by the loss to understand if this value is actually lower than the minimum between sigma L and C. We can normalize like these values by the perfect forecast. So basically, if the buyer had perfect knowledge of the future, earlier purchase may be put in place only when the cold spell takes place, guaranteeing the minimum possible expense. So the perfect forecast guarantees an expense which is sigma multiplied by C. So using all these values, basically, we obtain the value of the forecast in percent, given by knowing the expenses due to having no info, so to a business as usual strategy, minus the expenses using the forecast, divided by the same minus the perfect, the expenses having perfect knowledge of the futures. Goes without saying that if this value is lower than this, we have a negative value, which means that the forecast doesn't hold any value. And this is like the same thing in a graphic form. We can see in the y-axis the forecast value in terms of basically percentage. And here, since we don't have, as scientists, we don't have an exact idea of how much it is the cost and how much it is the loss, we can put in our x-axis basically the ratio between cost and loss. So here basically the forecast has no value, because that means that the cost is very low with respect to the loss. Then the buyer has no interest in considering the forecast outcome, and he will always purchase the hazelnuts in advance since the cost is very low. In this area of the graph, again, the forecast has no value, because the early price is so high and so similar to the loss that the buyer will always risk to incur a loss, because purchasing the hazelnut in advance is not a viable option. And again, he won't use the forecast outcome. But for all cost to loss ratio in this area, basically we have a value of the forecast. So these lines, these full lines, are the ones for Western Black Sea and Eastern Black Sea, representing the target weeks 1 and 2. And we can see that, of course, for target weeks 1 and 2, the forecast has higher value, up to 60%. So that means that for certain users that have a cost to loss ratio around 0.2, more or less, the gain that we have by using a seasonal forecast is 60%. But also for prediction made 3 to 6 weeks in advance, we have potential economic value imparted by the forecast for users that operates in a cost to loss ratio in this area. So even when we have basically a very low skill for near surface temperature, a cold spell forecast can actually be of benefit for a certain type of end users. So this is basically the main conclusion of my talk, and yes, you can read it. So this work has been done because assessing the economic value of cold spell forecast could be crucial for the hazelnut agribusiness, which is characterized by low spatial diversification. Most of the hazelnuts are cultivated in Turkey, and very sensitive to extreme cold occurring during flower development. And a multi-system subseasonal forecast was put in place to predict the occurrence of such extreme event in northern Turkey, home of about 70% of the global hazelnut production. And the multi-system show comparable or better skill than single models. The fact that poor 2-meter temperature prediction skill after week 2 does not prevent the forecast from being valuable and usable if we use a targeted cold spell index instead of 2-meter temperatures. And the potential forecast economic value is large for a number of users who may benefit from the use of subseasonal forecast instead of taking no action. In both the Turkish production areas, as expected, lead week 1 and 2 have more intrinsic value than further lead weeks. However, even forecasts supplied 3 to 6 weeks in advance may result in up to 25% economic gain for the agribusiness operators. So this work is in review, and you can hopefully find it published in a decently short time, and if you're interested, I will let you know. Thank you very much.
Oh, thank you, Stefano, for this presentation. We collected a couple of questions, so I would start with Paula Vesco from Uppsala University in Sweden. She asked two different things. The first one is more related to the ensemble modeling and the performance of the ensemble modeling. So specifically, she asked how about the metrics that you use to evaluate this performance. If you used only the correlation to the real temperature, or if instead you evaluated the ability of your model to correctly predict the number of cold spell episodes. She also suggested that there are several methods that you can use, for example, the AUC, so the area under the curve, or the precision recall, or the Brier score. So she wonders about really the performance assessment. While the second question that she poses is more related to the economics behind. So in your cost model, the total cost borne by the buyers result from a multiplication of cost by predicted versus real cold spells. So the mathematical formula that you showed at the very beginning. So she wonders if you've considered weighting this expression. For example, the cost of a false negative, so cold spell which occurred but was not predicted by the model, can be perceived by the user differently from basically the cost of a false positive. So predicted cold spell but not occurred. She also said that it was super interesting, so she really looks forward for the paper to be out.
Great. Thanks very much. Both are very pertinent questions. So about the first one, so we did not perform any verification for the cold spell. I think it is a very good question. We only perform verification for like the global scale. That was because like we wanted to be sure that the forecast that we had put in place was in fact reliable, was discriminating, and had high like resolution. And to do this, we didn't perform only the deterministic score, which is the only one that I showed in this presentation, but we also perform probabilistic scores, in particular the ignorance score and the rock score. And so instead, the analysis on the cold spell is the one that actually I had shown, and somehow the number of cold spell, counting the number of cold spell, is actually what we have done by constructing the contingency table. And about the second question, yes, I totally agree. The Garrity Skills course, as I don't know if you see my screen, so the Garrity Skills course basically assign the same value to false alarm and missed events. So this, of course, is not exactly what is meant for particular end users, because, for example, a missed event could be much more devastating than a false alarm for an end user. So this number should be actually modulated according to the needs of the end user themselves. However, we decided to follow the framework of Garrity without changing it, because this is not exactly an economic estimation of the damages of a cold spell, but it's just a potential economic estimation which is able to give to us the value, an intrinsic value to the forecast. Of course, like having more detailed data, because I mean we are working in a framework where for example, the horizontal resolution is 1.5 degrees. So basically, the areas that we are selecting in our nut simulated nut farms are much bigger than the real ones. So in having better a better framework, we could and better information by the end users about the damages that can come from a false alarm or from a missed event. Of course, we can improve this framework. But this is a first attempt to give an intrinsic economic value to the sub-seasonal forecast.
Okay, thank you. We have another question from Malcolm Mistry from Ca' Foscari University. He introduces his two questions because he has two, saying that it was a very nice presentation. So Thank you for attendance, and I just want to recall that in general, you can access this webinar again on the CMCC YouTube channel, so don't hesitate to actually revisit the CMCC webinar page to actually revisit the webinar. But coming to Malcolm's question, the first one relates to the way the cold spell power index is measured. So it's measured in degrees Celsius, which means that basically it's an index at discrete time step. So he wonders if it does take into account the consecutiveness, which could be important for hazelnut, in addition to the frost, for example, in a particular day or on days spread across days spread apart. While the second question is instead related to how many times is there a similar validation exercise that was undertaken in different regions in the world, and if you could elaborate on that. Thank you.
I'm sorry, Francesca, I didn't understand the second question.
The second question was about the presence of a similar validation exercise in other regions of the world. So if instead focusing only on Turkey, if there was another exercise in a different region.
Okay, thank you very much, and both actually very nice questions. Thank you, Malcolm. So about the first one, no, we did not took into consideration. Sorry, there is a noise. Okay, I'm sorry. So we did not take into consideration the duration of the cold spells, and this was specifically because actually, you know, like the cold spells many times occur, first of all, only during, you know, like these cold spells that are devastating in this area in particular are occurring only in the nights. And even, you know, like one night with temperature well below zero can be destroying for the flowers. So like the fact that we aggregate basically the results in chunks of 1 week, of course, excludes these cold spells that are very short and like not very intense. But if we have a cold spell that only lasts 1 night, but it is very, very intense, it can be detected by this methodology, even aggregating like the outcomes in weekly chunks. And so basically the duration for like the specific reason was not taken into consideration. Of course, like this cold spell power index could become a cold spell, for example, severity index, in which we take into consideration also the duration, but for this exercise we didn't find it so important. And about the other question, actually no, we did not use this methodology in other areas of the world, but of course I am very open to, you know, like share my codes and my expertise in this with whoever is interested for, you know, like to compute other similar studies in other areas of the world.
So my question from me is more related. You said that you started this exercise because there was a very specific request from a big player in the industry, right? So it is a very interesting case of making like science usable and useful for decision making. So I was wondering how was, if you can tell more about the experience that you had from the user perspective. So you basically presented this work, and what was the main challenge that you encountered in this user interaction and in this sort of exercise in presenting the results of your analysis?
Yeah, so actually, like we had a very good experience with the end user we worked with, because they, like the person we talked to were very, like, first of all, very educated in terms of, you know, like agronomy and partly climate and hydrology sciences. and also they were very much available to listen and to give us all the freedom to basically face the problem from our point of view without giving us any constraint. Of course, the main challenge concerns the language that we use, that sometimes is a little bit too heavy for end users that actually want to have a result explained in simple words. And sometimes we have the impression that they wanted something that it was impossible to achieve. So the fact, for example, if we look at this contingency table, so one of so now let's look at this one, for example. We look at this contingency table. So one of basically the doubts that the users had was, but I mean, like in this case, like you are predicting the cold spell when it actually occurred only 8 times, while 10 times you didn't predict the occurrence of cold spell and it actually did, or 18 times you did wrong. So basically you did wrong 28 times and right only 8 times. So this was a little bit what they were wondering. So like, what's the use? What is the use of this product if you are wrong more times than the times you are right? But first of all, actually we are right, actually not only 8 times, but we are right 86 times out of this 114, for example. So this is like something that we have to explain to them, even if they are not very much interested in this result. But then even if like most of the times actually when the cold spell occurs, we are not able to predict it, like in this case, for example, where out of 18 cold spell, we only predict 8. These values actually show with the cost loss model, in fact, is actually very clear in showing that even if we are not extremely good in predicting this cold spell, there is still an intrinsic value of the forecast, which is better than using nothing, using no information. So in the end, after a lot of meetings, a lot of exchanges with them, they actually appreciated much the result of our research.
That's very interesting. We're giving the floor, the audience, the ability to send a couple of questions, if any. Otherwise, your contacts are very available on your professional page, but anyways, we recall them again, stefano.materia@cmcc.it. This work hopefully will be published, but is currently under review. Please check the CMCC YouTube channel if you want to listen to Stefano's very clear explanation again. And for the rest, if there are no more questions, we're actually able to close. So thank you for attending. There are more than 50 people still online with us. And thank you, Stefano, for your presentation. Hopefully meeting you all again on November 12th. Thank you again.
Thanks.